Hello everyone, and welcome to the MLOps workshop. In this video, we are going to be getting hands-on with packaging a model using MLflow. We are going to see two different approaches to doing this, and we'll explain the benefits and downsides of each. So let's get started by first discussing what MLflow is. It's a really broad framework with a lot of useful tools, but it has three main components: MLflow tracking, MLflow projects, and MLflow models. The MLflow tracking component is an API and a UI for logging parameters, code, versions, metrics, and output files when running your machine learning code and for later visualizing the results. An MLflow project is a format for packaging data science code in a reusable and reproducible way, based primarily on conventions. And finally, an MLflow model is a standard format for packaging machine learning models that can be used in a variety of downstream tools. The format defines a convention that lets you save a model in different flavors that can be understood by different downstream tools. The last component, MLflow models, is what we will be learning in this video. So let's get started. Alright, so let's package a model. So here I just have a standard notebook with the BERT pre-trained language model. I'm just going to use this as an example, but you can think of this model being a sentiment analysis or any kind of model really. So we'll pip install the necessary packages. We'll import our packages, and up here again I'm just mounting my G drive so that I can save out data artifacts. Here we're just loading in the BERT tokenizer from pre-trained, we're loading in the BERT model from pre-trained, and here we're using the tokenizer to encode just some sample text. We use this just to see the output of the language model. Okay, and now using the sample text, we'll throw through the language model and see what comes out. Alright, so here we have the output from the language model. So now let's package this model. Alright, so remember we pip installed MLflow up top here. So let's go ahead and import these. Okay, so like I mentioned at the beginning of the video, we're going to be seeing two main ways to package a model using MLflow, and both have their benefits. So we'll start with using this mlflow.pytorch.save model. So there's a PyTorch specific serialization call here. So what this takes in is our model, and it takes in a MLflow path. So this is the output path where it's going to save these data artifacts. And the third parameter here, we can see conda env. This is where we would store all of the requirements for our model. So we have PyTorch as a requirement, we have transformers as a requirement, MLflow. So this is where you would store all of that so that in your deployment environment, you can actually replicate this exact environment that you created the model in. So let's go ahead and run this. Okay, so now if we do an ls on that directory, so we can see three different artifacts: MLflow model, data, and conda.yml. So now let's load this back in, and just to make sure everything's working properly, so we can see new model, mlflow.pytorch.load model. And we just, just like when we were saving, we just pass in the path to the data artifacts. Alright, so we didn't get an error there. And this input IDs, this is the same sample text that we used up here. So if we run this, we can see we get the same output. So we saved the model and we loaded the model back in. But this use case isn't really beneficial. I mean, we saved it and then we loaded it back into the exact same environment. The purpose of packaging up a model is so that we can ship it off and use it and load it in a different environment. So now what I'm going to do is I'm going to download these artifacts that were created to my local computer, and we'll walk through pulling this package in, setting up the environment, and loading in the model. So like I said, I've gone ahead and I've downloaded our model. So let's again take a look at the contents. We had conda.yaml, data, and ML model. Okay. So I downloaded this, and now I have it opened up in a directory. So what do we have here? We have our ML model file, our conda YAML file, and this is our serialized model. You can see it's it's a large file. It's going to take a while to open, and it's not really going to be human readable. Okay, so as I mentioned, we have this conda.yaml file so that we can specify what requirements were necessary in training the model so that we can replicate that environment in a downstream deployment. So if you remember, we had PyTorch was a requirement, transformers was a requirement, MLflow is obviously a requirement. So now that we have this on a different system, right? This isn't the notebook that we created this in. Let's see how we would actually use this package now. So what I'm going to do is run conda env create dash file, and I'm going to point it to this conda file. This is how we'll get the same environment here as we had when we created the model. So let's let this run. So we can see that our conda environment has been created successfully. So let's go ahead and copy this command. And I also wanted to point out that I mentioned that we have this ML model file here, but what this actually is, if we go back to the documentation, we can see that each MLflow model is a directory containing arbitrary files together with an ML model file in the root of the directory that can define multiple flavors that the model can be viewed in. So that's really what this file is all about. We can see there's flavors up top here, and we have two flavors, a Python function flavor and a PyTorch flavor. Don't worry too much about the specifics of this file. We'll dig into it deeper a little bit later. Okay, so now that we have our environment or our conda environment created, let's activate it. All right, so now we have our conda environment up and running. We can see mlflow.env, which was the name that we gave it in the conda YAML file. So we can do a quick pip list, and we can see we have transformers present, we have torch present. So now this environment is an exact replica of the training environment in which we created the model, which is what we want. So I went ahead and I've created an app.py file, and this is where we're going to load in our model. So what are we doing here? We're going to import torch, we're going to import my mlflow.pytorch. Remember, this is the command that we used to save the model, mlflow.pytorch.save model. And here we're going to be using load model. We're going to import transformers, and here we have model equals mlflow.pytorch.load model. We're going to give it the directory that we want to pull our model in from. Notice that we're not giving it a /data/model.pth file. It's one of the nice things about using MLflow is it has standard conventions where you just you give it the root directory and it knows where to find everything. So here again, before we can send text into our language model, we have to tokenize it first and convert it to torch tensors. So here we are, tokenizer again, getting our input IDs, and let's go ahead and give this a run. All right, so here we can see the output from the language model, negative 0.0549, and if we go back here, we can see we had the same exact output in our training environment. Yeah, so that's great. So this is awesome, but there's one thing that I don't particularly like about this setup, and that's that we have to import the tokenizer, this transformers package, and we have to import this tokenizer or recreate this tokenizer here. See, this tightly couples the serving logic with the model logic, right? It would be a lot nicer if we could also somehow serialize this tokenizer in with the model, so that really all we would have to do is, say model equals load model, and then perhaps model.predict, right? And then have all of this pre-processing logic happen inside of the serialized model itself. That way, like I said, we decouple the serving logic from the application-specific logic. So this is going to be the second approach that we investigate, and we'll see why it leads to a little bit more of a cleaner solution on the serving front. So the way that we package up all of our pre-processing or post-processing logic alongside our model is by not using the mlflow.pytorch call anymore, but now we're going to use the mlflow.pyfunc method. Using this isn't as easy as calling mlflow.pytorch.saveModel, but it gives us a lot of power in that we can package up all of our any kind of additional logic right together with the model. So the way we use this is it's a little bit different. So there's a few required parameters here. One of which is that it's convention that our model has a predict function on it. So we can look back at the PyTorch models. Here we're essentially just adding input directly to the model call, right? So here's our model, we're adding the input directly into this. We're not calling .predict. So with using the pyfunc methodology, you have to create a predict method off of your class. And the interface for this is it's going to take in a pandas data frame. Okay, and then there's one other required parameter that we need to make note of, and that is the load pyfunc method. So we can see here we're in mlflow.pyfunc.saveModel, and there's a few required parameters. So one of which is we have path here to where we're going to save the Python model, and now we have this loader module. So the name of the Python module is used to load the model from data path. So this model must define a method with the prototype load pyfunc. So if we want to use our mlflow.pyfunc methodology, we have to include a load pyfunc method off of that class. And we'll see why in a minute. So here we are. So same similar setup to before. So we're going to have an output path, and here I'm a little bit different. I'm just calling torch.save on our model and torch.save on the tokenizer. Remember how we said that I wanted to wrap up this pre-processing logic. So we're serializing the model and the tokenizer. And then down here we have an mlflow path, this is where we're going to save our data artifacts in here. So that's where we're passing in the path. Here we're giving it a loader module. So this is what we just previously discussed, the loader module. And it'll become more clear in a second what this is actually doing. A data path. So this is the path to any kind of additional serialized logic that we want to add to the model. So this is where this pyfunc data directory, this is where I was saving the model and the tokenizer. So that's where we're going to point the data path to, right? This is data that we want to pull into our model, or pull into our package, I should say. And then we have a code path and a conda environment, just like before. So the two main new things here is this loader module and code path. And you can see both of these are referencing this wrapper model, which I'm importing here. So let's this isn't a pip package. This is a Python file that I created. So let's see what I've done in wrapper model. Okay. So in here, notice a few things. So at the very bottom, right, we have this method load pyfunc. It takes in a path. And inside of this method, I'm calling model torch.load. So this is loading the model that we serialized up here. Then I'm calling tokenizer equals torch.load. So I'm loading in the tokenizer that I saved out to disk. And then I'm returning this model wrapper, and I'm just passing in the parameters model and tokenizer. And the model wrapper is a class. Right? It takes two expected inputs. So this one takes tokenizer. You can imagine if you're in any kind of tabular data set, you're going to have categorical features with a label encoder. You can package that up and pass it in just like we're doing with this tokenizer. So when we initialize it, we're setting our model and tokenizer values. And then, as I mentioned, we also have to have a predict function off of this class, or method off of this class. So here we are, predict. It's going to take in some data. And if you remember, this data is supposed to be a data frame. Okay? So data, and this should look familiar, right? Input IDs, torch.tensor, self.tokenizer this time, right? We're not explicitly calling BERT tokenizer from pre-trained and then tokenizer.encode. This tokenizer is what we've serialized out to disk. Dot encode, and then here I'm just using, if you're familiar with pandas data frames, I'm just calling iloc 0. That's just grabbing the first instance from the data frame, and I'm grabbing the text from a text column off of this data frame. And then we're just going to, just like before, return input IDs and grab this. So this is what the wrapper model looks like. And this is how MLflow enables us to package in external logic, outside of what's just in the model, and package it all up together. So if I go ahead and run this, it's going to save out this package to my my Google Drive, and then we can load it back in just to test to make sure everything worked properly. Like I mentioned, it's supposed to take a data frame, so we're going to create a pandas data frame. We're going to use the same text, so here's some text to encode as we used up top here. Here's some text to encode. And I'm setting columns to text because inside of our wrapper model, we're expecting the text column to be on the data frame. So let's exit out of this, and then if I call mlflow model.predict and we pass this in, we get the same output value from the language model as before. So just like previously, again, this isn't super interesting because I'm loading a model back in the same environment that I created it at. So what I've done is I've downloaded it to my local computer, just like I did before. So this was our previous app.py, right, where we're taking in the tokenizer and getting the output from the model. So now I have two more items here. So we have a PyFunc model, right? And in here, just like in the other one, we have an ML model file. But this time, inside of data, we have a few more objects. We have a model.pt and a tokenizer.pt, right? This is what we serialized to dict over here. And we also have this code directory this time. And in here, we'll see, here's our wrapper model.py. Okay, so this is the same code that we were looking at over in our Google Colab notebook. Model wrapper, we have our load pyfunc, we're loading in, so this takes in a path and then it's loading in two data artifacts, and it's just instantiating this class with those as parameters, and then here's our predict function. So now if we look at here was our previous app.py, right? We load in our model using mlflow.pytorch.loadModel, our tokenizer. Now all we have is model equals mlflow.pyfunc.loadModel. We give it the directory where all of our data artifacts live, and then now all we do is we create an inference data frame, and we just call .predict on the model. So if we run this, so here we end up with the exact same output as we did with this model, which is the exact same output that we had over in our Google Colab notebook. So that's MLflow. We'll definitely dive into it more throughout the workshop and hands-on sections, but I hope that you can see how powerful this mlflow.pyfunc process is, how we can abstract away any arbitrary amount of pre-processing or post-processing logic, and we can package it all up into this single artifact, and where all we have to do is say load me in and call .predict. So yeah, that's MLflow, and I hope you guys enjoyed it.